Ha! Here we are.
It'd be awesome to cook Thanksgiving with you because then it'll never get done. We always end up starting talking about random stuff.
I'm way worse in the afternoon. So, uncertainty analysis. We're finally there. Chapter 5. We're done with statistics. But oh wait, we're going to use statistics to determine how uncertain we are. Okay? We have confidence. Now let's find out about certainty. All right. We have learned about confidence from a statistical point of view. Based on sample variability, we might have p% confidence in a given measurement. As we have learned, an estimate of the variability of the random variable x, in this case the measure n itself, is given by its sample standard deviation, Sx. In the case of multiple samples, the best estimate was the sample mean of standard deviations, right? The best estimate of the value x, that is, its mean, mu x, was the sample mean. In the case of multiple samples, the best estimate was the sample mean of sample means, right? Sweet. Finally, the best estimate of the variability of the mean was the sample standard deviations of sample means, right? Also called the standard deviation of means because we don't like saying sample over and over again. We just get lazy. We just say standard deviation of means. Further recall the nice estimate of the standard deviation of the means from a single sample with size n. Do y'all remember this? Oh, fat marker every time. No matter how many times I do it, I will do it again. Not the quadratic formula. No.
Every time.
You'll be right one day.
In engineering, you'll be right like 30% of the time if you just say quadratic formula.
Not in my classes.
How certain you were then?
Terribly.
So, this was our nice formula for estimating the standard deviation of the means from a single sample standard deviation. Remember, you can also simply take the sample standard deviation of the standard deviation of, the sample standard deviation of the mean values when you have several samples. But if you have just one sample, you can estimate what the standard deviation of the mean would be if you took a lot of samples and took their means. So there you go. It's a nice little formula. As we can see, as sample size n increases, the standard deviation of the mean decreases. We went through this whole discussion before, but I'm trying to remind us of that. This type of error in a measurement is called random error and gives rise to random uncertainty, S, related to what we have called confidence intervals about the best estimate of the mean, such as for a single sample of size n. So we say that x, a value of the random variable big X, is going to be an element of this interval. So we take the mean of our sample and then we say it's near that mean. It's plus or minus the sample standard deviation of the means multiplied by the t-value. The t-value being dependent on, remember the t from the student's t-distribution, where nu is the what? Do you remember? The what?
No. You said what nu was, and I was like, nah, viscosity, because that's technically what nu is. But
Oh, you mean in a different world where you guys talk about fluids? Yeah, no. When we're considering statistics, it's the degrees of freedom, right? And it's related to the sample size, n. When we're estimating things that are variance or standard deviation, the degree of freedom is n minus 1. And then p is the percent confidence we want to have in this interval. And then S is standard deviation of S x bar is standard deviation of the means. So this is our confidence based on the probability P of a student random variable x taking on a value x within T standard deviations of the mean. Right? Well, that's what we did. That was like one of the big things we built up to in that chapter was being able to have a confidence interval with a certain confidence that was essentially the probability of that thing occurring, assuming that the random variable had a normal distribution for large n or a student's t distribution for smaller sample size n. So that's what we got. And so the random uncertainty S is very much related to that. It's just a half interval. So we just say the random uncertainty is t times the standard deviation of the mean. So it's this guy, right? It's the amount that you would go up and down to create your confidence interval. Okay, that's what we call our random uncertainty. So we're going to, actually this chapter essentially is going to build up to a point where we're going to be able to use this in conjunction with the next part, which is the other type of uncertainty. Alright, so the standard random uncertainty, which is just, this is sort of just like a terminology thing. The standard random uncertainty is simply one standard deviation of the means for high n, meaning we assume it's a normal distribution this time, and we want to go one standard deviation. One standard deviation in a normal distribution is 68% probability for your confidence interval, and we have that the z-score essentially is 1, the t-score for high n, or the z-score, their equivalent, is just 1, and we get what's called the standard random uncertainty, S. All right. However, error can arise from more than just randomness. Okay? Other sources arise that bias the measured values, say up or down, from the mean. This is called systematic error and generates systematic uncertainty B. And the reason we use B is because bias. B for bias. S, you might be like, oh man, because S we use for the random uncertainty, but S and S for systematic, like they should go together. But S is actually meant to be like standard deviation, right? Like in this case, just a standard deviation, or in this case, it's some multiple of the standard deviation. So S is supposed to like conjure up standard deviation. That's how I justify it. And then B, this is just the book's terminology, and I've just adopted it because I don't want to confuse you guys more than I already do. So, okay. All right, so we have the, great. So our systematic uncertainty or bias B. For instance, a scale might be systematically reading high. I know my scale does, especially around the holidays. This can be identified and mitigated by calibration to a standard. The National Institute of Standards and Technology, NIST, calibrates weights, and that is a link to their website, and they tell you all about it. They're very proud of it. I mean, they should be. Good for them.
Don't recycle.
Just use your
Try harder. It's more clicks. You need more clicks.
I'm calling this click.
No, it's because you guys have PDFs of them, so you can click the damn links. Okay. I could probably put a footnote with the URL so you could type it in. I could do that.
Have you uploaded this stuff?
Well, I tried to, but my script broke, which is why it was taking so long, so I ended up going around it.
Yeah, that's what
So the link doesn't work yet, smartass. Will work eventually. You guys have just way too much sass back there. Seriously. Okay. So let's say you have a 10 kilogram NIST calibrated weight because the link worked with one normal standard deviation confidence plus or minus 200 times 10 to the minus 9 kilograms, which I literally got from their website. That's what their one standard deviation confidence is in the 10 kilogram calibrated weight from NIST. So I wanted to make, I mean, it's pretty good, right? 10 to the minus 9 on 10 kilograms. It's pretty good. All right, so let's say I weigh it several times on my scale, and the sample mean is 10.5 kilograms. We could conclude that my scale has a plus 0.5 kilogram systematic error. Or would it be plus 5%? Because really it's 5%. It's also 0.5 kilograms. So that question, I think, brings up an important point when we talk about bias. The systematic error could change depending on the operating point, so care should be taken when extrapolating. So it might be 0.5 kilograms at 10 kilograms, but at 20 kilograms it might be, say, 1 kilogram, and maybe it's proportional. Or maybe it's not proportional either. Maybe it's some other function. So we can really only have confidence when we're near the place that we have calibrated, right? So we use this sort of thing, a standard, to calibrate our scale. So then when I look at my scale, I would say, oh, I need to subtract 0.5 kilograms, or maybe there's a little adjustment I can make on the scale to bring it to 0, or bring it to the right value, 10 kilograms. Either way would be fine, but we have to make sure that we're recognizing that the systematic error might not be some constant value. It might depend on the scale that you're working with, the value that you're measuring, and we'll see an example of that today. Actually, there's an example that we'll do. So in this chapter, we explore different ways to quantify uncertainty, beginning with the so-called design stage, at which we estimate uncertainty based on minimal information with little or no data, and working to the more advanced sample stage, which is my term, not the book's term, because I hate their term, at which we estimate uncertainty from the information used before, but include that of multiple measurements. So they call this like multiple measurement uncertainty. But their handwriting's better. Okay. So I really like this book, but I'm gonna call them out. I don't like this term. I think it's a poor term. So great. I'm calling it sample stage because we're sampling at that point. We're using the sample to come up with the estimate of uncertainty, so therefore we're calling it sample stage. If you guys think of a better word, let me know. This is clearly going to become, whatever I choose here in this class for these notes, is going to become the preferred vernacular for the rest of the engineering, at least English-speaking world. So we should get it right. So if you guys have you guys have an opportunity right now to really, contribute to the terminology of measurement theory hereafter. So something to think about. Mull it over. Maybe over the weekend you'll be able to figure out a good term for the rest of time. All right.
I'll be honest, most of the measurements of late come from a pencil and a ruler, so measurement theory is not exactly strong.
The pencil stage? Okay. Yeah. We'll work on it.
How well
We'll
did I
work on it.
sharpen the pencil?
All right. So let's go on to the next lecture.